Thank you for coming early. I have to admit that over breakfast someone reminded me that I speak at 9 and not at 9:30, and had it not happened I would have shown up late to my own talk. So I want to discuss something that is very close to the theme of this conference, which is the issue of randomness and primes. And I want to discuss randomness in angles of Gaussian primes. So let's go back to a compatriot of some of the people here, Pierre de Fermat, and he showed that primes are sums of two squares if and only if either the prime is 2 or the prime is congruent to 1 mod 4. I think it was only Euler that gave a formal proof, but certainly Fermat stated it and probably knew roughly how to do this. So half the primes are sums of two squares. And for such primes, we can express them as the norm of a Gaussian integer, which is itself necessarily irreducible as a Gaussian integer, that is a prime Gaussian integer. And this representation as a sum of two squares is essentially unique. You can, of course, switch the roles of A and B and change their signs, and that's it. So there's essentially a unique way to represent such a prime as a sum of two squares. So you take the corresponding Gaussian prime and write it as in a complex form in terms of the radial part, which is the square root of the prime, and an angular part, the argument of this Gaussian integer. So we make this argument unique if we assume that A and B are positive and that A is bigger than B. So you get a unique angle between 0 and pi over 4. And what I want to do is to understand this sequence of points in the unit interval, or in the interval between 0 to pi over 4, as you vary over all primes which are 1 mod 4. So I want to know, does this look like a random sequence of points? That's the goal. So here is a picture of several hundred such Gaussian primes, where for each such prime I took all 8 representations. So you can try to look for yourself and decide whether or not it's random. Okay. Now I only want to look at the angles, so here is a depiction of angles of the first 67, not the first, of 67 consecutive Gaussian primes, and you get the sequence of points between 0 and pi over 4, and I want to understand, is this random or not? Now the first result in this game is due to Hecke from 100 years ago, and it says that this sequence of points is uniformly distributed. So in other words, if you fix a subinterval and look at how many such angles, what is the proportion of angles which lie in this particular subinterval, then in the limit as you take more and more primes, you should recover the relative length of the interval. That's uniform distribution. Okay, so what I'm going to compare these angles to are random points. So I take, for instance, n points between 0 and pi over 4, chosen independently and uniformly. And I compare the various statistics that I have for random points with the statistics I can deduce or experiment with for these particular angles. So from some points of view, these angles are not random. Well, of course they're not random. They are God-given. We have the primes. There's nothing random about them. So here's the first statistic. Let's look at the maximal gap between the first n angles. So let's compare. If you take the maximal gap between n random points, let's say in the unit interval, it's a problem in probability theory to understand how this grows as a function of n. The average gap would be 1 over n. So the maximal gap will be somewhat longer. The question is how much longer? And this is a question that was debated in the probability literature. As far as I know, Paul Levy in the 1930s determined the behavior, and almost surely the maximal gap behaves like log n over n, so slightly bigger than the average gap, but still somewhat bigger. And what we can show here, and this is the proof, I will go over it, is that the maximal gap between the first n Gaussian angles is much, much bigger than what it is for random angles. So there's a gap of size 1 over root n, roughly, between the first n angles. So instead of log n over n, you get 1 over root n, so a much bigger gap. So I need to prove something in the talk, so here is the proof. This is well known, it's not mine. I'm sure this was known to Fermat. Okay, so here's the proof. I'm going to show that there's a forbidden region around 0, that there's a huge region around 0 which has no Gaussian angles, not just of primes, of any Gaussian integer. And here's the proof. So you take an integer, which is sum of 2 squares, most x, and we want to put it close to the number 1, to have angle close to 0. So if the angle is close to 0, then it looks like it's tangent. And the tangent is b over a. And because these are integers, b is at least 1. Okay? So you get something which is at least 1 over a, and a is less than root x. So you get something which is bigger than 1 over root x, so the angle is at least 1 over root x, and the number of primes up to x is x over log x. So that proves that you get something like this. This is completely elementary, but it uses something about integers. So from this point of view, these Gaussian angles are not random. The maximal gap is much bigger than for a random sequence. Okay, now let's look at the minimal gap. So if you take n random points in the unit interval, what is the size of the minimal gap? The maximal gap is log n over n. The average gap is 1 over n. Well, there's something called the birthday paradox that says that the minimal gap is going to be 1 over n squared. So if you take the unit interval, divide it into m boxes, and put n points in there, when will you have high probability of having 2 points in one box? So if you have a class of, okay, a number of students, what's the probability you have 2 students with the same birthday? It's not 1 over 365. It's much smaller. And so the answer is that you need roughly square root of 1 over square root of the number of students. So the minimal gap between n points in the unit interval for random points is almost surely of size 1 over n squared. And here, the minimal gap is actually much larger, and I'm leaving this as an exercise to you. It's the same argument as we had in the previous slide to show that there is repulsion between these points. They want to be far away from each other. The minimal distance between 2 angles where the primes are less than x is bigger than 1 over x. which is x, number of primes up to x is n over log n, so it's 1 over n log n. So the minimal distance between points is much, much larger than for random points here. So from this point of view, Gaussian angles are also not random. On the other hand, these statistics of maximal gap and minimal gap are not robust. If you look at the points on the paper and try to measure them, and the fly comes and sits there accidentally, it completely screws up these statistics. It can introduce a very small minimal gap. So let's look at a more robust statistic. And here I have, before what I gave you was exercises. Now here's an exercise I have no idea how to do. So the question is, if I look at the typical gap, not minimal or not maximal, what is the distribution function of a typical gap? So this is a non-trivial procedure you have to do. You take the first 1,000 primes, each of them gives you an angle, but these angles are not ordered. You don't know which comes first. So let's order these angles. You order them, and then you look at the difference between the first and second point as it comes down. You don't know which prime it belongs to. So you look at these consecutive gaps. So these points are n points in the unit interval. You think that the average gap, by definition, is 1 over n. So let's blow it up by dividing by this 1 over n. So you get something which has a chance to have all to be of size 1. By definition, its average value is 1. And we want to understand the distribution of these points. So that I am looking for the probability distribution function. It's called the level spacing probability. And here's what it looks like for random points. For random points, there's an exercise you need to do that says that this level spacing distribution is exponential. Okay? And here's the proof. I just generated 5,000 random points in the unit interval and did this ordering. It's quicker than actually proving something. And you see a reasonably good fit. Therefore, it's a theorem. So we moved to Gaussian angles, and I did the same experiment. I looked at all primes up to 1,000,000, which are 1 mod 4, got these angles, ordered them, and computed this histogram of normalized nearest neighbor gaps. And I don't know what the answer is. So I leave this to future generations to understand, or maybe to someone 5 minutes after my talk, to understand, is there a limit? Question number 1, is there a limit? Question number 2, okay, a physicist won't ask question number 1. The real question is, what is the limit? So is it going to be the random limit, or is it going to be something else, or none of the above? I don't know, I'm just putting it all out there for you guys. Okay, so we went from an exercise to the state of my ignorance. Okay, so let's go up a few scales. What I was doing until now was look at statistics at the finest possible scales, at the scale of the mean spacing between points. But now I want to take steps back and look at much cruder statistics on much larger scale. So let's go back to Hecke. So uniform distribution means that you count how many angles lie in a fixed interval as you put more and more angles down, and the answer is the number is proportional, the ratio of the number which lies in this interval to the total number of points you get is the relative length of the interval. And this is what uniform distribution means. This is uniform distribution. You fix the interval. But now I want to look what happens in shrinking intervals. So what I was talking about, the level spacing distribution, was intervals which shrink like 1 over the number of points. That's very, very short intervals. I want to look at longer intervals now, but still shrinking. Now, to have a chance of finding finding an angle in such a shrinking interval, I can't take the intervals to be too short. So if I have 5 points and I divide the unit interval into 1,000,000 subintervals of equal length, usually these intervals will not contain any of the 5 points. So I don't want to do this. I want to put more points than I put subintervals. So the length of the interval had better be bigger, significantly bigger, than the 1 over the number of points. And then you hope to get some kind of statistics. So I want to look at intervals which are significantly bigger than 1 over x, where I look at primes up to x. And then once you look at such intervals, you can ask, does this asymptotic still hold? Is the proportion of angles which lie in such a shrinking interval the same as the relative length of that interval? Now, what transpires is, and this either Hecke or people who came after him knew, that if you assume the generalized Riemann hypothesis, then this asymptotic continues to hold as long as you look at intervals of length slightly bigger than 1 over square root of x. So uniform distribution is interval of size, of fixed size. The limit of what you can imagine asking is intervals whose length is 1 over x, where you look at primes up to x. And GRH says that every short interval of length bigger than 1 over x to the half will contain prime angles and will actually contain the correct proportion of prime angles. So this is what you can do assuming the Riemann hypothesis, and then there was a series of work by Kubilius and his school in Lithuania, who tried to do an unconditional version of this statement and got some exponent which is between 1.5. And relatively recently, Glenn Harman and Lewis got a better exponent without equidistribution by using sieves rather than zero density theorems. Now, the important point for me is, since I believe in the Riemann hypothesis, I don't really care right now about what happens without it, but I want to emphasize that the Riemann hypothesis actually gives the best result on this problem. It says that intervals, every interval of length 1 over square root x will contain the right number of prime angles. And we saw this big hole, which was size 1 over root x, which does not contain any angles. So you cannot do better than the Riemann hypothesis gives you. It's kind of remarkable here if you want to compare it to the situation with primes in short intervals. So primes in short intervals, the Riemann hypothesis would say that if you look at intervals of size square root x around x, then they will contain the right number of primes. But we expect that every short interval whose length is bigger than x to the epsilon will contain the right number of primes. Let's say 30 years ago, people expected better, but had to change their mind after Meyer's work. But so there, the Riemann hypothesis can only get us half the way. Here, the Riemann hypothesis gives us the honest truth. You cannot do better than that. So it's kind of remarkable from that point of view. Now here's a question that people should have asked, and maybe did ask. Instead of looking at the worst possible scenario, what happens in every short interval, you can ask what happens in a typical short interval. So in the theory of primes, there's a famous theorem of Selberg that says that every short interval whose length is slightly bigger than the mean spacing between the primes will contain a prime. I think he has to assume the Riemann hypothesis for that. Not I think, he has to assume the Riemann hypothesis for that. But if you give up on individual results and go to almost all kind of results, then you can actually get at the truth in this theory of primes. So you can ask this question here. What happens if you look at Gaussian angles in short arcs, but not in every short arcs, but in almost every short arcs? And then the answer is that if you assume the Riemann hypothesis, then almost all short arcs, as short as possible, essentially, will contain the right number of Gaussian angles. Now, this result has to be in the literature, but we couldn't find it, and then by some serendipitous process, which involved osmosis between walls of adjacent offices, both Ezra Waxman, my student, and I, and independently Peter Sarnak and Ori Parzanchevsky came up with this fact that almost all short arcs contain a Gaussian angle. So this is assuming the Riemann hypothesis. One should be able to do something unconditional, and the goal here would be to go below what you can do individually. So I would want almost all short arcs of length less than 1 over root x contain a Gaussian angle to do better than what I can do on GRH. In any case, if I want to show something happens almost surely, one way to do it, it's not the only way, but one way to do it is to study the variance of the corresponding quantity and then to use something like Chebyshev's inequality or your favorite version of it. And the goal I had when I started working on this with my student Ezra Waxman was to actually study the structure of this variance. I didn't realize that people didn't seem to know this almost everywhere result. I was sure that it is known, and I wanted to understand the quantitative form of these statistics in comparison with random statistics. So here's the basic quantity. This is what my talk is really about, the number variance. So you take this interval between 0 and pi over 4, where all the angles lie, divide it into 1,000,000 equally sized intervals, and you get a random variable, which for each of these intervals, these bins, you ask how many of the n angles fall into that bin. So n is the number of angles I have when you take primes up to x, which is half x over log x. And you just count how many of these angles are in an interval whose relative length is 1 over k, where k is the number of bins that you have. By definition, the expected number, the average number, is the total number of angles divided by the number of bins. So it's n over k. That's by definition of an average. And what I want to understand is the fluctuations of this random variable from its expected value, meaning the size of the variance. This is the variance here. So I average over all intervals of length 1 over k. I look at the mean square, and I want to know what is the size of the variance. Now, for n random points, so here's another exercise. If you take n random points, there are 2 models of random points. The one I indicated, which is the Bernoulli model, you just take n independent uniform points. Another model which is very similar is to take a Poisson process with that same intensity. And in both cases, the variants are similar, and certainly when n over k is big, then they are the same. And you get something that the variance would be n over k. That's a Poisson model. So what we can show here is that, assuming, again, the Riemann hypothesis, the variance is bounded by essentially n over k times some logarithmic factor. Okay? Now, if you have something like that, then we use the Chebyshev inequality or some other thing to deduce. So you know the variance is small, you can deduce that almost all arcs of length 1 over k contain a prime angle as long as there's a chance for it to happen. So that's how you show this almost everywhere result. You just give a good bound for the variance. You don't need something as good as that. but this is what the Riemann hypothesis gives you, so you're happy. So what I want to do is to understand how this variance behaves relative to the variance of random points. So here's the conjecture. The conjecture is that it looks like random points if the number of bins is relatively large. So if you look at very short intervals, then the conjecture is that the variance will look like those of random points. But there's something else happening if you look at longer intervals, so if you look at few bins. So if k is relatively small, and the cutoff is the following. So I look at the ratio of the variance to the random variance. So in the random case, the ratio is 1, like this. That's a red thing. And what I believe happens here is that this ratio, when you plot it on a log scale, if you compare it to the ratio of log of the number of bins to log of the number of points, will display a transition. It will initially, so if you look at very short intervals, meaning the number, so if you look at long intervals, so the number of bins is small, it will be linear. And then when you take bigger, more than the square root of n bins, so the intervals will be less shorter than 1 over square root of x, you will transition to the random behavior. So that's a conjecture, and here's the proof. So the scatter plot, I took 35,000 angles, did this division into bins, and computed the empirical variance. And so you certainly see deviation from the random thing. You see a reasonable fit. It's not fantastic, I should say. This is a lousy plot. I wouldn't dare show it in a physics conference, but you guys take anything. So this looks like a reasonably good fit. There's still a bias. And then there's something that, if I was a betting man, maybe I would say looks like this. Okay, so that's the proof. So where do I get this conjecture? So here's the conjecture. The blue line is the conjecture. The red line is random. The scatter plot is what happens for some number of points. And I didn't generate this conjecture from numerics, I have to admit. I first had the theory, and then like any good physicist, you run and try to find the justification for your theory by doing an experiment. So I came to this conjecture by two independent approaches. One is to express this variance in terms of zeros of a certain family of L functions, and then replace whatever I get for the zeros, replace the zeros by eigenvalues coming from a suitable ensemble of random matrices. I will not explain anything about this here. And the real point was to go make a function field model and actually prove something in the function field model. And this is what I want to explain now. Okay, and then you need to have a dictionary to tell you how to go from function fields to number fields. This is something that I know how to do. So what is the function field analog? So instead of looking at the integers, we look at polynomials over a finite field. Okay, we've had a couple of talks about finite fields here. So the polynomials over a finite field have many properties in common with the ring of integers. They are a unique factorization domain. There's a Euclidean algorithm. You can talk about primes, which means irreducible elements. Instead of positive integers, you take monic polynomials, and then you would be trying to count, instead of counting the number of positive primes up to x, you would count the number of monic irreducible polynomials of given degree. And so instead of the prime number theorem, you'll be talking about the prime polynomial theorem, which I'll mention a little later. And then instead of looking at sums of two squares, you would like to express polynomials as some quadratic form in two variables, and I chose this particular one. You want to express a polynomial as a square of a polynomial plus t times another square of the polynomial. There's a reason for this particular choice, which I am not going to discuss. So instead of adjoining the square root of -1 to the integers to get the Gaussian integers, you adjoin the square root of -t to your polynomial ring and get another polynomial ring. So I haven't really changed the theory here, which is a quadratic extension of your base polynomial ring. And I will try to mimic these questions about angles in this context. Now, what is the advantage for me here? That this function field theory is perturbative. There is a parameter that I can change, and that's the size of the finite field underlying everything. I cannot perturb the integers. I think someone said that God gave us the integers, Dedekind or someone like that. Kronecker, some guy who had the likelihood to think of it. I cannot perturb the integers, I can perturb polynomial rings. And this is the great advantage. There's this semi-classical parameter that allows me to do that. Okay, so instead of Gaussian integers, I adjoin the square root of -t to the ring of polynomials in T. I just get another polynomial ring. It's a little artificial from this point of view. There's still a notion of complex conjugation, which is Galois conjugation, the Galois involution of this quadratic extension, which is just take, if we denote by S, I forgot to say this somewhere, S would be square root of -t, you just replace the polynomial at square root of -t by the polynomial at minus the square root of -t. And then the norm would be the product of the polynomial and its conjugate, its Galois conjugate. So it's now a polynomial in T and not in square root of -t. What is important is to have an analog of an angle. Now, I don't know angles, but I know the unit circle. So the analog of the unit circle here would be to look at all formal power series with unit norm. Because the unit circle is the set of all complex numbers with unit norm. Okay, and then you put some extra condition which is useful but not important for our discussion. And now I want to look at the analog of an angle, which is a direction. So to a complex number, I can write it as its length times a direction vector, an element on the unit circle. And I can recover it by looking at the ratio of the complex number to its complex conjugate. I'll get the square of the direction. And this is what I can do here. I look at the ratio of the polynomial to its complex conjugate. Turns out I can extract the square root in this group. And that gives me the analog of e to the I theta. So you have to believe that this is a useful thing to do, I have to admit. And then I have to have analog of short arcs. And this I can also do. I can put a norm on the set of formal power series. You take the valuation that comes from infinity. There's a way to do it. And it turns out that two such elements are close if they are congruent modulo the kth power of the polynomial involved. There are several ways to get at this thing. This is the natural thing to do. So you take this unit circle, divide it into k sectors. There's a relation between k, this capital K, and this little k, which is not important. The details are not important here. And now I want to play this game of asking, among all prime polynomials of given degree, how many have their angles, have the direction lie in a specific sector of this non-Archimedean unit circle. Again, the details don't really matter. If you haven't gone into this, it's not useful. So I want to do it for prime angles. So there's the fact, the analog of Fermat's theorem, that a monic irreducible polynomial is a norm in this ring, so it's a squared plus tb squared, if and only if its constant term is a square. The proof of that is exactly like the proof of Fermat's theorem. So in other words, it's a norm in this ring where I join the square root of minus t to this ring of polynomials in T. And so among these polynomials, I want to know how many polynomials of given degree have a direction in a particular short arc. So this is my counting function. The expected value of this count function is the total number of all polynomials of given degree. Let's call this n, that's my number of points, divided by the number of bins that I put them into, by definition. And the number of points is the total number of prime polynomials of given degree. And the prime polynomial theorem says that it looks like q to the degree over the degree. This, by the way, is an exercise. For people who've read Hugh's book, they can do the exercise for primes. But for prime polynomials, I hope this will be an exercise in the second volume of Montgomery and Vaughan. Okay, so here's the theorem. The variance in this polynomial setting, and again, the details are not really important for us, can be computed. It's a theorem in the limit of large finite field, in the limit of q going to infinity. And the answer is, here's an answer. So the answer is, well, essentially 1 if you take very short arcs, if you take many bins. And it's essentially twice the ratio of log of the number of bins to the log of the number of points. There are some correction factors which I will ignore right now. And this is the same, why it's interesting for me, it's the same as my conjecture for what happens over the integers. Okay. It's not a coincidence. I first did the polynomial thing and then I used that to generate a conjecture. But you have to A, be able to prove something like this, and B, have the correct dictionary. That is the point of what I was looking at. So I now have two proofs of this blue line. One is this numerical scatter plot, and the other is this function field correspondence. Okay, so I have 1 more minute and 4 more slides, which is fantastic. So being in France, let's do an impressionist version of how to prove this. So 4 slides in 1 minute. If I talk more, then I will do it in half a minute, just so that you see what kind of mathematics comes into this. It's not the usual kind of number theory. So slide number 1. In order to pick out primes and progressions, I need Dirichlet characters. It turns out that in order to pick out, you're not going to be able to follow any particular detail here, so don't try. So in order to pick out these prime polynomials with directions lying in a certain sector, you need a particular kind of what turns out to be Dirichlet polynomials with a very special modulus and a very special condition, which I call super even. Again, you shouldn't think too much about the details. It turns out to be the analogues of Hecke-Gaussian characters. I didn't realize it until much later than that. So there's a definition. And then the statement is that 2 polynomials lie in the same sectors, even if and only if these Hecke-Gaussian characters agree on them. That's the first slide. The second slide is that to each Hecke-Gaussian character, I associated an L function. That L function is known to satisfy the Riemann hypothesis because of the work of André Weil. It has a trivial zero and then a lot of non-trivial zeros. So I write these because I know where they are. I know the Riemann hypothesis. I write this L function as the characteristic polynomial of a matrix, which is unitary. That's the Riemann hypothesis here. It's called the unitarized Frobenius matrix. It comes from somewhere, but I'm not explaining this. And then the first result you have to show is that you can express the variance of this counting function in terms of these zeros of this collection of L functions. In other words, as the average of a certain function of these Frobenius matrices. Again, the details don't matter. And then the second step is you want to know something about the statistics of the zeros of this collection of L functions, in other words, of these unitary Frobenius matrices. And for that, I asked my friend Nick Katz to try to investigate it, and he showed that these Frobenius matrices become uniformly distributed in the appropriate compact Lie group, which happens to be the unitary symplectic group in this particular example. And that allows me to replace this average in the limit when the finite field is going to infinity by an integral. And then I compute this integral, I make a dictionary, and I get this answer. So this, in 1 minute, was the proof. So to summarize, I studied these Gaussian angles, and I have a conjecture for the number variance with some support. Thank you.